Now we're going to talk about differential equations. This is going to be a fairly substantial topic. We're just going to get started today. So we've already talked about difference equations, and I'll just remind you that's telling you how to go from xk to xk plus 1, and so you sort of follow along one step at a time. And now if you imagine doing a difference equation where you let the intervals be small, and in the limit you make them smaller and smaller, well, then you're getting a differential equation. That is to say, I'm describing a function for you by telling you how it changes going from each step to the next, and infinitesimally the change is given by the derivative. These tangent vectors are giving you the rate of change. So it's clear that the sort of continuous version of a difference equation is a differential equation. So the equations we're going to be looking at are going to be like this. U of t is a function of t, a vector function of t, for example, with two coordinates. And you think of this as being a path in the plane. As you vary t, you get different points in the plane. And you can think of this as being governed by some physical property. And if you have that, you take the derivative, u prime of t, which is u1 prime, u2 prime. That's giving you the tangent vector to this curve. And so a differential equation, an example of a differential equation is like this. I'm saying that the tangent to the curve of u is given by this matrix A applied to u, and if you write it out in coordinates, it's a pair of ordinary differential equations like this, which are linked because u1 and u2 both occur in both of these equations. So here's a very simple example of that. Take a diagonal matrix. The equation is then u1 prime of t is 2u1 of t plus 0 u2 of t, and u2 prime is 0 u1 of t plus 3 u2 of t. So they're not really linked. You can solve them separately. And it's clear that the solution is e to the 2t. u1 is e to the 2t, and u2 is e to the 3t. And you're allowed to put some constants in front, and you can write it like this. All right. Well, let's talk about the more general case. Suppose I gave you a differential equation du dt is a applied to u, u of t. Well, I'm going to make a crazy guess here. I'm going to guess that u of t is, the solution is an exponential, e to the at times some fixed vector u naught. That's just based on the previous example. The exponential should be coming in here. And, well, let's just wing it here. I don't know what the exponential is, but let's pretend it exists. Then let's check. The derivative of u of t would be the derivative of e to the at u naught. And if we're lucky and this exponential behaves the way it's supposed to, when you take the derivative of an exponential, you pull down the coefficient, which in this case is the matrix A, and you get this, which is indeed A applied to this thing here, which is the original vector u of t. And indeed, at least formally, I've found a solution. And so that just gets us to the question, what is this thing e to the a of t, really? How do you make this actually work? Okay, so let's take a little bit of time to talk about these matrix exponentials. So A is an n by n matrix. What is e to the a? Well, obviously it's supposed to be, by analogy with the ordinary exponential, this power series, 1 plus a squared over 2, and so on. And that's perfectly fine. The question is, does this really make sense? It's an infinite series, and the answer is yes. This infinite series converges. That's the big main fact that we're using here. So, for example, if you had a 2 by 2 matrix, AB, what is e to the a? Well, it's the identity matrix plus a squared over 2 and so on, and it's just really happening coordinate-wise. You're getting e to the a, e to the b. So for diagonal matrices, it's just the exponential of the diagonal. And what is t, e to the ta, where t is a real number? Well, by definition, that's 1 plus ta plus ta squared over 2, and so on. And now let's write down some facts about e to the a. One of the basic properties of the exponential is that this, e to the a, e to the b, is equal to e to the a plus b. But for matrices, there's a crucial fact here. It's only true if a and b commute. ab has to be equal to ba. And the most common way that this can happen is if b is equal to a, and you get something like this: e to the a times e to the a is e to the 2a. Or you can use a and minus a. Those commute, so you get e to the a times e to the minus a is e to the 0. And let's see, what is that? That's the 0 matrix. So it's 1 plus 0 plus 0 and so on. These are all matrices, and you're getting the identity. So that shows that the determinant of e to the a is not equal to 0, because e to the a is invertible. I just told you what its inverse is. E to the a inverse is e to the minus a. So that's kind of a cute fact. E to the a is always invertible, just like the ordinary exponential is always non-zero. And another basic fact is that the derivative of e to the ta is you pull down the a, just like for the ordinary exponential. And finally, if you can conjugate by s, it's the same as if you conjugate it on the exponential or if you conjugate it in the exponent. That's easy to see. So that tells you how to compute e to the a. If you have a matrix A and you know it has, well, the simplest case, it has n eigenvectors and eigenvalues, and you make this matrix S out of the eigenvectors as usual so that you can diagonalize A, we know how to compute the exponential of a diagonal matrix. So we can use this to compute the exponential of A as follows. What is e to the a? Well, let's see. A is SDS inverse. So e to the a is e to the SDS inverse. And you can pull the conjugation down. And we know e to the d. So that is a good way to compute e to the a. And we also conclude that e to the at, if you just put the t in there, and this vector u naught, is s e to the dt s inverse u naught. And this is just like something we did in the setting of difference equations. All right, so that's all preparation for the big theorem from this section. And it goes as follows. Suppose we have an n vector u of t, a function of t, and we have a matrix, an n by n matrix A, which has a basis of eigenvectors, lambda 1 v1 through lambda n vn. And we consider the differential equation du dt is equal to a u of t. How do we solve this? Well, I already told you the answer to this. It's u of t is e to the at u naught, where u naught is some arbitrary starting condition. That's what we did before. But now this is the new thing. Here's another way to write this. It's a linear combination of these exponentials, e to the lambda 1t times v1 plus dot 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 and cn e to the lambda nt times vn. So it's an arbitrary linear combination of the eigenvectors with these exponentials in front, e to the lambda t, where the lambdas are the eigenvalues. So obviously these eigenvalues are going to play an important role in the behavior of this differential equation. That's enough for now, and I'll talk more about this next time.